Welcome to AP Bio, and today we are learning about carbon.
All right, very good. You might have the job, Joe.
Thank you, Mr.
You might
Jones.
have the job. All right, so I'm going to kind of start back from the beginning of carbon and review what we went over yesterday that you guys were hurting on the quiz, right? So when we start learning about nutrition and we start learning about the molecules that we are going to consume in our diet, and those molecules that we consume in our diet are going to become the different parts of our body. In order to understand those molecules composing our diet, we first have to understand the role of carbon in organic molecules, right? An organic molecule is defined as any molecule that contains carbon, right? Anything that contains carbon is considered organic. So even if you look at something weird like methane gas is CH4. Is methane technically an organic molecule?
It is.
Yes, absolutely. Is water organic? No, right? It is not, because it does not contain carbon. Now, we said in class yesterday that carbon contains special properties, or it performs a special function. And here we always go back to that relationship that we will see over and over and over and over again in this course. And that is the relationship between structure and function. Right? So somehow the structure of carbon is going to give rise to all of its special properties, all of its functions that make it essential for diversity in life. Carbon displays tetravalence, right? Meaning that it has 4 valence electrons and can therefore bond with 4 other atoms, right? This is going to allow carbon to form the backbone of all organic molecules, right? The backbone is the core central structure, right? And when you look at this diagram on the board, highlighted in blue is the backbone of various different organic molecules. Since carbon has tetravalence, it's able to create a wide variety of different backbones, right? You can have linear chains, you can have branching chains, you can have carbon rings, you can have double bonds, you can have triple bonds, you can have all these unique arrangement of carbons. I want you to write something down. There are 2 factors that determine the properties of an organic molecule. There are 2 factors that determine the properties of an organic molecule. First, number 1 is going to be the arrangement of carbons in the backbone. Right? Number 1 is going to be the arrangement of carbons in the backbone. The arrangement of carbons in the backbone. Why? Because the arrangement of the carbons is going to determine the what of that molecule? The shape or the structure, right? It's going to determine, in my mind, shape and structure mean the same thing, right? It's going to determine the shape of the molecule. And the shape of a molecule determines its what? Its function, its properties, what it's able to do. Right? And today is all about that relationship between shape and properties. I'll give you an example of something that we'll see often. Something that we call hydrocarbons. Hydrocarbons are long chains of carbon and hydrogen. All right? So a hydrocarbon chain would look something like this. carbon, 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 carbon. And you have a whole lot of hydrogens, right? Do you see how these are all hydrogens? So this would be a hydrocarbon chain right there. Now, first of all, I'm going to ask Alex this question. I know he knows his chemistry. If you're looking at a hydrocarbon chain, is that going to be polar or non-polar? It's a tricky question. You think hydrocarbons are polar or non-polar? Go with the other one.
Non-polar.
Non-polar. Right, do you see a positive and a negative side? What do you see? Do you see any negatives or positives in what I drew? No.
They're all neutral, I think.
Right? Yeah, there's no negative, no positive. You have no distribution of charge. And if you have no distribution of charge, is that going to be polar or non-polar?
But doesn't there have to be charge somewhere so the atoms can actually be attracted to each other and form the hydrocarbon chain?
Well, we're talking about the molecule as a whole. We're not talking about the formation of the molecule. So if you're looking at this hydrocarbon chain, yeah, you have a ton of covalent bonds, right? And you need interactions to form those covalent bonds. But when we're looking at if a molecule is polar or non-polar, to be polar means that you have sides, meaning that you typically have a negative region and a positive region, or you have some type of unequal distribution, right? That is why water is a polar molecule, because when you look at water, it has that partial negative and that partial positive side, right? It's got an unequal distribution of charge. Do you see that at all with the hydrocarbon chain? No, right? Hydrocarbons are non-polar, right? That's important to understand. They are non-polar. And you can see right here, what do we find hydrocarbons in? What type of molecule? What does it say? Fats, right? Fats are made up of hydrocarbon chains. And we know that fats are what? Polar or non-polar? Non-polar. Do they dissolve in water? No. We refer to them as being what? Hydrophobic, right? Water-fearing. I want to give you guys a major hint. Sean, this question's for you. If you are looking to see whether a molecule is polar or non-polar, what atom would you look for that would indicate that it's polar?
Oxygen.
Oxygen, right? Oxygen. Whenever you see oxygen, you can make a good guess that that molecule is probably going to be polar, because oxygen contains what property? It's electronegative. So if you want to look for polarity, you want to look for electronegative atoms. And there's a couple. Oxygen, for our purposes, is the most electronegative. Nitrogen is also electronegative. Sulfur is actually also electronegative, but not as much as oxygen. Do you see any of those in a hydrocarbon chain? No. Is carbon electronegative? No. Is hydrogen electronegative? No. All right? Not at all. When you look at a molecule, where is all the energy stored in that molecule? Go ahead, Aaron. It's stored in the bonds, right? When you look at a hydrocarbon chain, you see a lot of bonds or a little bit of bonds? A whole lot of bonds. So do you think fats have a lot of energy or a little bit of energy? They have a whole lot of energy. You look at fats and you think back to calories we've been talking about, right? Fats have 9 calories per gram, where carbs and proteins have only 4. So fats contain more than double the amount of energy than carbs or proteins do. And the reason why fats have so much energy involved in them is because they are composed of hydrocarbon chains that have a ton of chemical bonds, right? That is why fats are so rich in energy, way more calories than anything else. It's all tied in these hydrocarbon chains. So this is a good example of a relationship between structure and function. Another great example of that relationship is the study of isomers. You might want to write down the definition of an isomer. It's not on there. Isomers have the same molecular formula, but they have a different arrangement of atoms. So they have the same formula. They're made up of the exact same stuff, but they have a different arrangement. So really, the only thing that's different between them is going to be their what? Think about what we've been discussing. Their shape, their structure, right? They have the exact same atoms and the exact same numbers of atoms. But the only thing that's going to differ is their structure or their shape. So are they going to have the same properties? No. Right? By having a different shape, they're going to have totally different properties. There are 3 different types of isomers. And the first one is called a structural isomer. Structural isomers have the same molecular formula, but they have a different arrangement of carbons in the backbone. So here we see a good example. Both of these have the same molecular formula. They are C4H10. C4H10. So they have the same atoms, they have the same number of atoms, but they have a different arrangement of carbons in their backbone. They have a different shape. Are these 2 molecules going to behave the same way? No. They're going to behave very differently. They're going to have very different properties because they have a different shape, right? Because they have a different shape. So we call these structural isomers. Next, we have geometric isomers. Geometric isomers have, again, the same molecular formula. In this case, they have the same carbon backbone. They have a different arrangement of functional groups. Functional groups, I might want to write this down. Functional groups are the groups that branch off of the carbon backbone. Functional groups are the groups that branch off of the carbon backbone. Yeah. Functional groups are the groups that branch off of the carbon backbone. They branch off. Yeah. So when you look at this picture, the X's are just signifying where the functional group could be. And on this one, they're on the same side. And on this one, they're on opposite sides. Do we all see that? If they're on the same side, we call this cis. This is the cis formation. If they're on opposite sides, we call this the trans formation. So geometric isomers can have a cis form and a trans form. Have you ever heard of the term trans fats? You all heard of that? Pretty much the worst thing that you can put into your body is a trans fat. This is why we call it a trans fat. We'll look at their exact structure, but it has to do with the functional groups being on opposite sides of a carbon backbone. right? And that's what makes a trans fat. So it makes it actually so bad for you. Finally, we have enantiomers. Enantiomers are also referred to as stereoisomers. Two words for the same thing. Stereoisomers or enantiomers are mirror images of each other. They are left and right hands. So enantiomers are weird. They have the same molecular formula. Oh, I wrote it down right here. They look very, 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 very similar to each other. They're just mirrored. Do you think they're going to have the same properties? What do you think? Brock, what do you think? Are they going to have the same properties? Go with the other one. No. The reason why it's no is even though they have the same molecular formula, even though they look very similar, do they have the exact same shape? No. So are they going to have the exact same properties? No. I'll give you a good example. Have any of you heard of the disease, Parkinson's disease? We've all heard of Parkinson's, right? So Parkinson's disease is a disease of your nervous system. It's caused by a region of your brain called the substantia nigra, you don't need to know that produces a neurotransmitter called dopamine, which you don't need to know just yet. To treat Parkinson's disease, since you are unable to produce dopamine, we just give you dopamine. It's not entirely effective, but it is somewhat effective. We synthetically produce dopamine to give to somebody that has Parkinson's. Are we all able to follow that? Well, we call it DOPA. And there are two forms of it, and they are enantiomers. They are left and right hands. We have L-DOPA and we have D-DOPA. And they have the same molecular formula. They're just mirror images. L-DOPA, effective at treating Parkinson's disease. What do you think D-DOPA does? Absolutely nothing. Jack squat. It shows you the power of shape, of structure. You have two molecules that have the same atoms, same number of atoms, just have a slightly different arrangement that makes them a mirror image. One can be life-saving, and one can do absolutely nothing for you. Right? It really shows you the power, the importance of shape, right? Of structure, how important it is in biological molecules. Are we all doing okay so far? All right. So, tacos. All right. So we said there are two factors that determine the properties of an organic molecule. We said number one is the carbon backbone. Because the carbon backbone is going to give the molecule its what? Its shape. Number two, which you should write down, is going to be the functional groups. The functional groups. Those groups that branch off of the carbon backbone. The reason why the functional groups are so important is because they are the part of the organic molecule that is going to participate in chemical reactions. It's going to determine the reactivity of the organic molecule. Do you think the carbon backbone participates in chemical reactions? Based upon what I just said? No, it doesn't. Carbon backbone is just giving it its shape. It's these functional groups that are going to react. So I tell students the same thing every year. You don't have to have all these functional groups memorized, but you should be able to recognize them because we do see them over and over and over again. All right, so I want to go over some of the common functional groups. Number one, you have a hydroxyl group, OH, right? Same thing as hydroxide, OH minus, right? You find hydroxyl groups in things like alcohols. When you see hydroxyl groups, do you think that molecule is probably going to be polar or nonpolar? What do you think? You see a bunch of hydroxyl groups on the molecule. Is it going to be polar or nonpolar? What atom do you think do you see the hydroxyl group containing? Oxygen. So what do you think, polar or nonpolar? Polar. If you see hydroxyl groups, they're probably going to be polar. Think about it. This is ethanol, right? This is the molecule that we use to produce alcoholic beverages. Does alcohol mix in water? What do you think? Yeah, because it's what? It's polar, so it dissolves in polar water, right? Remember, if you're looking for polarity, look for oxygen, because oxygen pulls the electrons. It's electronegative. You guys all following me? It's hard to tell. Number two, carbonyl group. A carbonyl group is a carbon double bonded to an oxygen. Right? You see these in things like ketones and aldehydes. Right? We see them in this course. We don't see them like terribly often, right? But a carbonyl group is a carbon double bonded to an oxygen. Carboxyl groups, we see. Carboxyl groups have a carbon double bonded to an oxygen, and that carbon is also going to be bonded to a hydroxyl group. Now look at this picture right here. All right, Troy, you got good eyes? Look at this carboxyl group right there. What is it giving up? What is it donating as it goes from non-ionized to ionized?
The hydrogen.
The hydrogen, right? So carboxyl groups donate hydrogens. Do we all see that? And that would make a carboxyl group what? If you donate hydrogen, what does that make you? Donate hydrogen. Makes you an acid. Remember, acids donate hydrogen, right? They donate. They release hydrogen acids. So we're going to see a lot of carboxyl groups in all different molecules that we consider to be acidic. For example here, this is acetic acid. Acetic acid is vinegar. And is vinegar acidic? It's extremely acidic, right? Vinegar has a pH of like 2 or 3 maybe, right? And the reason why vinegar is acidic is because it contains the carboxyl group, which is going to donate hydrogen and make it acidic. Any of you guys drink kombucha? You ever hear of kombucha?
What's going on?
Kombucha is an energy drink. It's become really popular in the health field. But kombucha is fantastic for you. Yeah, I brewed kombucha for a long time. Really kind of cool. But a lot of the health benefits of kombucha come from the acetic acid that is being produced. Do you ever hear people taking shots of apple cider vinegar?
Yeah.
Right? Apple cider vinegar contains acetic acid, right? Which is that molecule right there, which is basically vinegar, more or less, right? And it's very acidic because it has that carboxyl group that's going to give up or donate the hydrogen. Good.
What happens if you drink the apple cider vinegar?
You're supposed to drink the apple cider vinegar, right? It's very healthy for you. It's good for your digestive system. Tastes disgusting.
Oh.
Absolutely, right? I'm not a big fan of vinegar. I find it kind of nasty, but it has its health benefits. The next group is an immunogroup. We see this a whole lot. Immunogroup is nitrogen attached to 2 hydrogens. And Troy, you have good eyes. Notice, what is that amino group doing? What's happening to it as it goes from non-ionized to ionized?
It's getting a hydrogen.
It's gaining a hydrogen. It's accepting a hydrogen, right? So amino groups accept hydrogens, which would make them what? Marcus, what happens when you accept hydrogens? You're considered a what?
Acid.
The other one. A base. Remember, we just learned this. Acids donate hydrogen. Bases accept hydrogen, right? So an amino group is basic because it is accepting hydrogen. I'm going to draw a really important molecule on the board. This is a molecule that you will become very familiar with. Carbon. Alright, here's an important molecule, right? What do we call this group right here? Amino group, right? That's the one that we literally just learned, right? And what do we call this group? Carboxyl group, right? And a carboxyl group is what? Acidic or basic? Acidic. You put an amino group with a carboxyl group, what do we create?
Amino acid.
An amino acid. And amino acids make up what type of macromolecule? Where do you find amino acids?
Right?
No. It's okay. We haven't learned yet.
Proteins.
Proteins. Right? Proteins are made up of amino acids. But this is why an amino acid is called an amino acid. The amino part comes from the amino group, right? The acid part comes from the carboxyl group, right? Amino acid, right? And these amino acids compose proteins, right? Arguably the most important macromolecule that we learn about, right? Proteins. All right, we doing okay today, guys? You guys are like struggling. Sulfhydryl SH, never see it. Don't worry about it. Last group, one that we will see many, many, many times, is the phosphate group, PO4. Phosphate group. Alex, this is for you, so I want you to get this one right. Phosphate group. Polar or non-polar? Polar. Super ridiculously polar because you see a ton of what?
Oxygen.
Oxygen. What are some molecules that have phosphate groups? Ellie, you said it before. DNA. Nucleic acids like DNA and RNA have phosphate groups. Phospholipids have phosphate groups, right? ATP has 3 phosphate groups, right? Phosphate, PO4.
If it's surrounded by oxygen, wouldn't it just be really electronegative and not polar?
Well, it's usually a part of bigger molecules, like ATP and a nucleic acid, right? So that's one functional group on a much larger molecule, and all those oxygens are going to be pulling the electrons from that entire molecule itself. Good question, really good question. All right, so these are some functional groups that you should be able to recognize, right? And they are important because they are the reactive part of an organic molecule. All right, so that completes our chapter on carbon. You have your homework for tonight. Now we move on to chapter 5, which is macromolecules. Can anybody tell me what the term macro means? Big, right? So macromolecules are the large organic molecules that compose our diet. And I can tell from our discussions that you guys don't really know much about real nutrition and what you are eating and what you are putting into your body and why you are eating it and what those things do. So within the next couple of days, I promise you, you will be enlightened. Right? I took a nutrition course in college and he called it the gospel of nutrition. Everything that you read in Muscle and Fitness and everything else is a big load of garbage. Right? Based upon selling protein powders and stuff. Right? I will teach you real nutrition. Right? But that's what we're focusing on.
Six-pack
Right?
abs.
These large macromolecules that we are going to consume in our diet. Joe, you're absolutely correct. And will eventually make up the different parts of your body. So when we look at these macromolecules, we're always going to be focusing on two things. Monomers and polymers. What does the prefix mono mean?
One.
One. What does poly mean?
Many.
Many. So when you look at a macromolecule, macro, big, you think macromolecules are monomers or polymers? They're polymers. They're really big. They're made up of many subunits. So each macromolecule is a polymer that is made up of many monomers put together. Right? So monomers are going to be the building blocks of polymers. So when we look at all these macromolecules, the carbs, the lipids, the proteins, we are going to be looking at their monomers, we're going to be looking at their polymers. Now, no matter what type of molecule that we are looking at, monomers are always put together the same way, polymers are always broken apart the same way. Right? These are two reactions that we will literally see over and over and over and over again. Number one is how we put monomers together to build a polymer. Now, Shaylin, looking at this picture here, if you want to put two monomers together, what do you remove? Water. You remove water, right? Do we all see that? We call this reaction dehydration. And that term makes a lot of sense, right? Because dehydration is the removal of water. Or we call it dehydration synthesis. So what usually happens, looking at this picture, is you have a hydroxyl of one monomer and a hydrogen of another. They are going to react, and dehydration synthesis is going to cause the formation of a what? What do we call that thing that links things together? A bond, right? Dehydration synthesis leads to the creation of a bond. No matter what, I don't care what we're talking about. If you are putting things together and making bonds, you are going through dehydration synthesis. So if you remove water to make a bond, how do you think you break a bond? You add water. Adding water is called hydrolysis. Hydrolysis, the addition of water, is going to break chemical bonds. Right? It's how digestion works. Right? You break apart your food chemically through hydrolysis, the addition of water. All right. I'm going to stop here. The bell's going to ring. This is a good stopping place for us today.